So in this video, I want to do a little review on parametric equations. And for number 13 in the book, I want to deviate a little bit from the instructions and just kind of talk about what a Cartesian equation is, how to find the Cartesian equation given the parameter t, and I'll briefly go over what a graph would look like if you're given some scenario. So to show you what a graph would look like and why parametrics are important, what they're used for is we can write these as functions of time. And we could do that using the parameter. The parameter is just some third variable t that usually means time, but it could basically mean anything. So let me just write that down. T is the parameter. Yes, okay. So let me set up a little table over here. X, Y, and t. So I'll go over here and I'll rewrite these as time functions. So x of t equals 4 times the sine of t, and then y as a function of time equals 2 times cosine t. So what happens, well, let's say when t equals 0, I drew this a little backwards, let me redo this. Alright, so t over here and x over here. So let's call t seconds. So when t is at 0 seconds, let's see what's happening to these functions here. So when t is at 0 seconds, for y, we plug in 0, and 2 times the cosine of 0 is just going to be 2, because we know the cosine of 0 is 1. And 4 times the sine of 0 for x will just be 0, because anything times 0 is 0, as we know. So when we look at this table, after 0 seconds, we've gone nowhere horizontally, but we've gone somewhere vertically, and we could call that meters. Like I said, it could really mean anything. It's just arbitrary at this point. So this could be, I don't know, let's say this is the ground, and we have a hot air balloon, and it's 2 meters off the ground. 2 meters off the ground. Okay, so that's just briefly to talk about what a parametric is used for graphically. But in a greater sense, with this third variable t, you can find the direction of an object or projectile. So if you have a car, I don't know, and it's driving off a cliff, you could say, let me just draw this scenario. If we have a car over here and it's driving off a cliff, very dramatic scenario, but it's driving off a cliff, and we could say at t seconds at this point in time, we could find exactly where it is. And that is the really cool thing about parametrics. So let's focus now on trying to find the Cartesian equation, and that could be confusing to some people what that really means. But a Cartesian equation is just an equation in terms of x and y. So slope-intercept form is going to be Cartesian equation, and most of the functions we're used to using. So let's go down here. Use blue. Alright, I actually need to look at this. Alright, so how would we go about finding an equation in terms of x and y? Well, let's think about it. So we could solve for t for one of these and then just plug it back in the other one, right? Let's try that. So solve this one for t. Of t. Alright, so, well, divide by 2. So we have y over 2 equals the cosine of t. Okay, and then to solve for t, we're going to take the inverse sine or arc sine of both sides. I prefer to use this notation. So the arc cosine of y over 2 equals t. So now we solved for t. So let's go ahead and plug that back into the top equation here. So now we have x equals 4 times the sine of the arc cosine of y over 2. Now, this technically is an equation in terms of x and y, but it's very ugly looking. It's not pleasing to the eye at all. It's very complicated. So let's try to look at this again and see, well, is there anything we can do that is going to kind of, well, we can make this easier. So whenever I see a sine and cosine, I always try to play around with those a little bit and think of my trig identities. So let's think about our Pythagorean identity, where we have the sine squared of, I'll use t because that's the variable we're working with, plus the cosine squared of t equals 1, right? Alright, so when we look at this, can't we just solve for sine of t and cosine of t and plug it right into this? So let's go ahead and do that. Well, we already found the cosine of t. That's y over 2. So we have y over 2 squared equals 1. And for sine of t, well, we just divide by 4. So sine of t is going to equal x over 4. So x over 4 squared plus that equals 1. So now hopefully this looks familiar to you. If we remember our conic sections, this is actually the equation for an ellipse. So this is an ellipse. Okay. So now this is much more easy to easy to graph and understand than this crazy thing. So let's go ahead and graph this. I don't know, use green. Alright. Just make this 5 by 5. Alright, so hopefully remember our conic sections. And now, when we graph ellipses, we know we have a major radius and a minor radius. So let me change to magenta. Alright, so when we simplify this out, we have x squared over 16 plus y squared over 4 equaling 1. So our major radius is just the square root of the denominator of the greater with the greater number. So in this case, 16 is our major radius. Well, 4 is our major radius. Take the square root of that. So major equals 4, and our minor radius is the square root of this one, and that's 2, and that's in the y direction. So our major radius is 4 in the x direction. So major radius 1, 2, 3, 4. And when we take the square root of something, remember it's plus or minus, so we have negative 4. Otherwise, it wouldn't be an ellipse. And 2 in the y direction. Then I'll sketch this as best as possible. Alright, and there we have it. This is the graph of an ellipse, and we found our Cartesian equation right over here. Hope that helps.